Okay, so what I'd like to do is I'd like to plot V naught versus VI for given this expression. Okay, so I'd like to plot V naught versus VI for these parameter values. Okay, so I'm going to pick Vs to be 10 volts, my dependent source parameter K to be 2 milliamps per volt squared, and I'll pick RL to be 5 kilo ohms. Okay, so this was none other than the start equation on the previous slide. So that's my V naught versus VI equation. And what I'll do next is I'll substitute the values above into this equation and I get this. Okay, notice for Vs, I've substituted 10. So K is 2 milliamps. So if I substitute K to be 2 and the 2 and 2 cancel out. If RL is 5 kilo ohms, then I get my 5 here, right? And then I have VI minus 1 whole squared out there. So let's plot this equation and see what it looks like. So let's go ahead and do that. So we've done this once before, so this should not be a big surprise. So I'm going to start with 10 volts here. And notice that as long as VI is less than 1 volt, then my VO is going to be VS. Okay, so VO is going to be VS, which is 10 volts for VI less than 1 volt. Okay, and this is true for VI greater than or equal to 1 volt. Okay, so for Vi less than 1, I get a flat part of the curve here where V naught is equal to 10 volts. Then as I increase the value of Vi, then notice that the curve begins to drop rather sharply because I'm subtracting the square of Vi from 10 volts. And so I get a curve that is going to drop, curve that is going to drop down like this. So where is the amplification here? Okay, so notice if I focus on, say, this part of the curve, okay, if I focus on this part of the curve, then notice that for a small change in VI, let's call that delta VI, for a small change in VI, notice that I have got myself a fairly large change in VO. Okay, so I get a fairly large change in VO, which I will call delta VO. Okay, so for a small change in VI, which articulates this part of the curve, I'm going to get a large change in VO. In other words, delta VO divided by delta VI, as you can see from this graph, is greater than 1. Okay, and this implies amplification. So if I can somehow take my input signal and boost it to this part of the curve, and you know how to do that now, you can apply a DC offset to boost a signal to this range here, then you will get that signal causing this part of the transfer curve to be active and give rise to a voltage gain where a delta VI becomes a delta V naught, where the ratio delta V naught by delta VI is greater than 1. So there's really not much else to do, but let me just go and wrap it up for you. I can also tabulate V naught versus VI for this equation so that we can look at some numbers in more detail. And so let me put down a little column here. So when VI is 0, when I substitute VI to be 0 here, then notice that I'm going to get my equation being one where Vs is 10 volts. Recall that this equation was true when Vi was greater than or equal to 1 volt. And I knew that V naught equals Vs when Vi was less than 1 volt. So as long as Vi is less than 1 volt, I'm going to get 10 volts at the output. So I get 10 volts here. So I go on up to 1 volts, I get 10 volts again. Okay, nothing particularly interesting happening here. Okay, so when I substitute Vi equal to 1, which is the threshold point, I get V naught equals 10 volts, and that's not a surprise. So what about when Vi is 1.5? So when Vi is 1.5 volts, then I get a zero point 0.5 here, and the zero point 0.5 squared is 0.25, and 0.25 times 5 is 1.25, and I get a minus sign here, so minus 1.25, and 10 minus 1.25 is 8.75 volts. Okay, I won't bore you with the details, and you can go check this out for yourselves. I can go ahead and fill the curve. So if this is 2 volts, I'm going to get 5 volts out here. If it's 2.1, I'm going to get 4 volts out here. If it's 2.2, I'm going to get 2.8 volts. If it's 2.3, I'm going to get 1.5 volts. And if it's 2.4, then I get down to almost 0 volts. Okay, so this is what I have. So right here, you can take a look at the value from, if you look at 2 volts down to 2.1 volts for the input, notice that this corresponds to a 0.1 volt change in VI. And correspondingly, notice that this results in a 1 volt change in the output V naught. Okay, so right there is a gain. So notice that in certain parts of the curve here, there is a gain if I'm careful as to where I go and pick my point to boost the interesting part of the curve so that the input will articulate that interesting part of the curve. Okay, so before I move on to a couple of final points, let me show you a quick little demo. And in this demo, I'm going to show you a circuit according that behaves similar to the one we've seen in our discussion so far, and do a little demo and show you what the output really looks like.